0, right? So the fourth row is now 0 row, and this is our new reduced row echelon form matrix. You can see this matrix is in reduced row echelon form. This is our leading entry, below that leading entry all the elements are 0. In second row this is our leading entry. You can see this column have only one non-zero element, other all are 0, either above or below. Third row, this is leading entry. Same situation happen here. In that column all are 0 except this leading entry 1. Okay, so now the null space of A is the solution of the homogeneous system Ax is equal to 0, and that is exactly the orthogonal complement of the vector space V. So now from this reduced row echelon form matrix we are finding the null space of A, right? The equation of Ax is equal to 0 is equivalent to Bx is equal to 0, and that's why from this reduced row echelon form matrix we are getting this equations: x1 plus x2 plus x5 is equal to 0, x3 plus x5 is equal to 0, and then x4 is equal to 0. Okay, so now in which column we don't have any leading entry? Second column we don't have any leading entry, right? And the fifth column we don't have any leading entry. So that's why there are two free variables, x2 is equal to k and x5 is equal to t. Because of second and fifth column does not have any leading entry, so that's why we are taking x2 is equal to k and x5 is equal to t. So x1 is equal to, you will get minus s minus t, x3 is equal to minus t. Okay, and now from this solutions, x4 is 0, x2 is k, x1 is minus s minus t, x3 is equal to minus 1 and x5 is equal to t. You will get the solutions can be written as x1, x2, x3, x4, x5, that is equal to, the value of x1 is minus s minus t, the value of x2 is s, the value of x3 is minus t, the value of x4 is 0, the value of x5 is equal to t. So the coefficient of s in all these 5 vectors, that is equal to minus 1, 1, 0, 0, 0 plus t into coefficient of t. In all these solutions you will get minus 1, 0, minus 1, 0, 1, right? So these two are basis vectors, and this basis vectors for the orthogonal complement of W, right? So here is the solution. The question number 4b complete. The next question 4c. Let R3 have the Euclidean inner product transform. The basis S is equal to V1, V2, V3 into an orthonormal basis where V1 is equal to 1, 0, 0, V2 is equal to 3, 7, minus 2 and V3 is equal to 0, 4, 1. So call it U1, U2, U3. Okay, so U1 is equal to 1, 0, 0. These three are basis vector, normal basis vector, and we are converting this basis vectors into a orthonormal basis vectors. And first of all we have to convert this three basis vector into orthogonal basis vectors, and for that we have to use Gram-Schmidt process. That process is called Gram-Schmidt process, and there are some formulas that call it this is U1, 1, 0, 0, right? Call it this is U2 and this is U3. Now V1 is equal to U1, let V1 is equal to U1. Now V2, what is the formula to find V2? Here is the formula, that is U2 minus inner product U2 V1 upon norm V1 square into V1, right? And the formula for V3, this is U3 minus inner product U3 V1 upon norm V1 square into V1 minus inner product U3 V2 upon norm V2 square into V2. So using these formulas we can find v1, v2, v3 such that v1, v2, v3 are orthogonal basis vector, and from orthogonal basis vectors to orthonormal basis vectors it's quite easy. Just we have to divide each vectors by its norm. Okay, so this is quite simple process, but important process is to convert this basis vectors into a orthogonal basis vector. That is a Gram-Schmidt process, and that is very important process. Okay, so call it v1 is equal to u1, that is 1 0 0, inner product u2 v1, that is equal to 3 7 minus 2 into 1 0 0, that is equal to 3. Okay, then norm v1 square, find norm v1 square, that is equal to 1 square plus 0 square plus 0 square, that is equal to 1. Now use this method. v2 is equal to u2 minus inner product u2 v1 upon norm v1 square into v1, that is equal to 3 7 minus 2. Okay, 3 7 minus 2 minus inner product u2 v1, that is equal to 3 upon 1 into v1, that is 1 0 0. Okay, so finally you will get 0, 3 minus 3 0, then 7 minus 0 7, then minus 2 minus 0 minus 2, so 0 7 minus 2, that is our v2. Now we also find v3, and for that we have to find inner product u3 v1 and inner product u3 v2. Now what is inner product u3 v1? Say u3 is 0 4 1 and v1 is 1 0 0. So dot product of these two vectors, that is 1 into 0 0 plus 0 into 4 0 plus 0 into 1 0. So you will get 0, inner product u3 v1, and then inner product u3 v2, that is dot product 0 4 1 into 0 7 minus 2. So 0 into 0 0 plus 4 into 7 28 plus 1 into minus 2 minus 2, that is equal to 28 minus 2, that is equal to 26. In a norm v2 square, that is equal to 0 plus 49, right, 7 square, because v2 is what, 0 7 minus 2, so 0 plus 49 plus 4, that is equal to 53. v3 is equal to u3 minus inner product u3 v1 upon norm v1 square into v1 minus inner product u3 v2 upon norm v2 square into v2. So u3 is 0 4 1 minus u3 v1, that is 0 upon 1 into v1, that is 1 0 0, minus u3 v2, inner product u3 v2, that is 26 upon norm v2 square, that is 53 into v2, that is 0 7 minus 2, right. So first of all multiply this coefficients with this bracket, so you will get 0 4 1, this is 0 0 into 1 0 0, that is 0 0 0, so you don't need to write this second step. This is 26 by 53 into 0, that is 0, 26 by 53 into 7, so that is 26 into 7, that is 182 divided by 53. This is 26 by 53 into minus 2, that is minus 52 divided by 53. So finally you will get 0 minus 0 0, 4 minus 182 divided by 53, okay, and that is 30 divided by 53, because 53 into 4, that is 212, okay, 212 minus 182, that is 30 divided by 53, and similarly 1 plus 52 divided by 53, so 53 take LCM, 53 into 1, that is 53 plus 52, so finally you will get 105 divided by 53. So these three vectors v1, v2 and v3 are orthogonal basis vectors. V1 is 1 0 0, V2 is 0 7 minus 2, and V3 is 0 30 50 0 30 by 53 and 105 by 53. Now these three vectors are orthogonal, that means the dot product of any two vectors, that is 0, that is equal to 0. But we are converting this orthogonal basis vectors into orthonormal basis vectors, and for that we have to divide each vector by its norm. So norm V1 is 1, norm V2 is, this is norm V2 square, right, that is 53. So norm V2 is equal to under root 53 and norm V3 is equal to square root of 11925 divided by 53. This you can easily find out, under root 0 square plus 30 square divided by 53 square plus 105 square divided by 53 square. So just using some numerical, you will get under root 11925 divided by 53. So the required orthonormal basis is given by V1 upon norm V1, V2 upon norm V2, V3 upon norm V3. So finally you will get 1 0 0, right, 0 7 by, you can see V2 is 0 7 minus 2 and divided by under root 53. So you will get 0 7 by under root 53 and minus 2 by under root 53. V3 upon norm V3, that is 0 30 divided by under root 11925 and 105 divided by under root 11925. So these three are basis vectors. Next question, question 5a. Is the vector 1 2 3 13 is in the range of linear transformation T, where T is defined from P2 to set of 2 cross 2 matrix. P2 means set of 2 degree polynomial, and this is 2 cross 2, set of 2 cross 2 matrix defined by T of A plus BT plus CT square, that is equal to A minus 2B plus C minus A plus 3B, B plus C, A plus 2B plus 5C. So now we want to check that this vector is in the range of the linear transformation or not, right? Now if suppose this vector is in the range of linear transformation, that means what? For some A, B and C, you will get this matrix, that is equal to 1 2 3 13, correct? Because of this matrix is in the range of linear transformation, that means for some ABC, this 2 cross 2 matrix, that is equal to 1 2 3 13, and then we have to find A, B and C. Then we want to find A, B and C. If suppose we can find such A, B and C, then definitely this vector is in the range of this linear transformation. But if we cannot find such A, B, C, such that this matrix, that is equal to 1 2 3 13, then this matrix is not in the range of the linear transformation, which is defined from P2 to set of 2 cross 2 matrix. So let's start. If the vector 1 2 3 13 is in the range of given linear transformation, then there must be a solution ABC satisfying A minus 2B plus C minus A plus 3B, B plus C, A plus 2B plus 5C, that is equal to 1 2 3 13. So comparing left hand side part and right hand side part, you will get A minus 2B plus C is equal to 1, right? Then minus A plus 3B is equal to 2, then B plus C is equal to 3, and A plus 2B plus 5C is equal to 13. Now to solve this 4 system of linear equations, definitely we have to use augmented matrix, and the system of equations is in the matrix form. If you want to write, this is matrix A, where A is equal to The first row is the coefficient of ABC, that is 1 minus 2 1. The second row is the coefficient of ABC, that is minus 1 3 0. The third row is the coefficient of ABC from the third equation, that is 0 1 1, and the fourth row is the coefficient of ABC in the fourth equation, that is 1 2 5. Okay, ABC, that is equal to, all are constant, that is 1 3 13, right, 1 2 3 and 13. So this is Ax is equal to B. The augmented matrix for the above system is the same matrix we are written here, then oblique and then this coefficients. Again we have to convert this matrix into a row echelon form. So that's why we are multiplying first row with 1 and add into the second row. So 1 minus 2 1, then the second row become 0 1 1. So this is 0 1 1. Also we are multiplying first row with minus 1 and add into the fourth row. So you will get 1 minus 1 0, 2 plus 2 4, 5 minus 1 4, 0 4 4, and this is 13 minus 1, that is 12. So 1 minus 2, first row is 1 minus 2 1 1. Now next process is we are multiplying second row with minus 1 and add into the third row. Also we are multiplying second row with minus 4 and add into the fourth row, and then multiplying second row with 2 and add into the first row. So here is our new matrix. First of all we are multiplying second row with 2 and add into the first row. So you will get 0 into 2 plus 1, so you will get 1. Then 1 into 2, 2 minus 2 0. Then 1 into 2 minus 1, that is 2 minus 1. Sorry, this is multiplying 2. So 2 plus 1, you will get 3. Then 3 into 2 6 plus 1, you will get 7 here.